Our third and final speaker today is David Kelf, who's the CEO of Breker Verification Systems. He's going to talk about top-down UVM-style test benches with PSS. Dave is a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys verification strategy, and run marketing for co-design, System Verilog, Novas, Verdi, and others. Today he serves as the CEO of Breker, the leader in test suite synthesis solutions. He has a solid engineering background, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University. Over to you. Thanks, David.
Okay, thank you, Sarah. And good morning or good afternoon, everyone. So actually, it's quite interesting watching Tim and Reese's presentation because if I look at my slides, it almost feels like I saw them before I wrote this because there's a lot of overlap, as we'll see in a second. So this is going to be interesting. I think we've all seen slides like this where we know that verification is a major part of the development flow. And indeed, in a Wilson research survey a couple of years ago, this is a survey run by Siemens EDA, we can see a large reason for this is because of creating these, the test content for these different environments, just takes a long time. And you have to wonder, why is this and what can we do to improve this? If we look at UVM today and System Verilog, of course, there's nothing wrong with UVM. It's actually a very strong standard, very effective, well used, and well liked as well. But what we see is that as for average size blocks, UVM works great. But when we're dealing with very complex blocks or large blocks or indeed subsystems, which might be multiple blocks on a fabric but without a processor, the use of UVM as it stands today is such that the complexity of the test bench can actually overshadow the verification intent that people are trying to create. And this gets even worse when we start to look at SoC verification and new needs that we see emerging in terms of performing SoC integration type testing, things like cache coherency and so on, and system validation and so on. So, as I think many of you probably know, the idea behind this portable stimulus standard was to create a solution for some of these issues, both in terms of trying to scale block-based verification better, and also increase the portability across the SoC design. We think that PSS does a reasonable job of this if implemented well. And indeed, Breker uses this today in our test suite synthesis flow. And in fact, I was enjoying Tim's presentation and Reese because if you take this flow here and turn it on its side, it looks almost exactly the same as the one that Tim presented, maybe with a little bit more color and stuff. But basically, what we do today in Breker's test suite synthesis flows, we take a model which can be created in a number of different formats, C++, portable stimulus, and this thing called system UVM I'll talk about in a second. Synthesize it, which is sort of similar to Tim's generation, generates a standard set of tests, which we then apply using some technology we call the synthesizable verification OS to different types of design platforms and different execution platforms as well. And the benefits of doing this are basically what Tim and Reese described, so I don't really have to go through them again. But firstly, things like the tests are self-checking. We can abstract the constraint usage to get away with some of the constraint complexity that Reese mentioned. Virtual sequencing can be included because the scheduling can be done on front. We can actually drive coverage as a constraint as opposed to looking at it after the fact. And because we pre-generate and pre-randomize the tests in the same way Tim was talking about, we can do things like drive emulation, we can optimize the tests, we can use AI and ML to pick out more efficient tests, and so on and so on. And finally, the tests become very portable. So we can use them with existing UVM test benches in the same way that Tim and Reese were mentioning, using agents and drivers. We can also spread them across SoCs, generate software for driving processors, and we can use them very effectively on emulation because we're not asking the emulator to do any randomization anymore. So there's a lot of benefits with pre-generation, pre-randomization of tests, you know, and I think Tim and Reese did a great job of talking about that. But there's a problem, and we've tripped over this many times in talking with different companies, and that is, you know, we're asking people to learn yet another new language of portable stimulus, which is somewhat different from UVM these days. So we see there's a lot of advantages to be gained, particularly for UVM block verification by using portable stimulus that we talked about before, if driven in the synthesis kind of flow. However, you know, today there's a lot of differences between PSS and UVM. For example, PSS is declarative, whereas UVM is procedural. The PSS approach is more top-down, where the UVM style approach is more bottoms up, starting with the design and creating tests around that. So, you know, while we really want to reuse and like and make the best of using our UVM test benches, the question is, how can we create a nice top-down flow with a synthesis style pre-generation, pre-randomization language, and still make use of all these PSS advantages? So we're working with 2 or 3 of our customers who have this same problem. Honestly, I wish I had $1 for every time someone has said to me, yeah, this is great, but why do we have to learn new language? We tried to see, can we put a UVM-style class library and some UVM utilities into PSS, much like the way the UVM class library is built into System Verilog. And so we try to constrain and set up PSS in a way that a UVM engineer would understand and would provide that kind of look and feel. And also make sure that we include some additional features, such as making it very easy to integrate top-down produce randomized test content into existing UVM test benches. And also make use of things like emulation and other mechanisms like that. So we've come out with this notion of system UVM, and it is simply that, a UVM-style class library utility built into PSS. So what is this? Well, basically, we take these UVM-style designs and we make use of the PSS graph-based models. We synthesize them and apply them into pretty standard UVM-style environments. And the kind of characteristics that the system UVM has is, firstly, we applied features such as TLM, to use TLM ports. We produced the RAL, standard UVM RAL register model, and loaded that into PSS. PSS today uses a different RAL model. We built in a lot of standardized kind of UVM types and messaging and functions that you might expect. We also made use of our verification OS to really tightly integrate this kind of style of test content from the synthesis tool directly into existing UVM environments and that can make use of UVM. And we applied an abstract constraint method to reduce constraint complexity in some of the kind of over-constraining issues that Reese actually mentioned. Just to get a little bit more detail, so from a transaction point of view, PSS today doesn't make use of TLM as such. You can apply it inside the exec blocks in PSS, but it isn't natively included in the language. So we basically built that back in. So you can use TLM transactions in the CLM standard with this system and apply those TLM transactions to regular UVM agents and VIP to apply them to design. So it makes it much more straightforward to do interfacing. The registers, as I mentioned, PSS today uses a different register model, and we certainly can allow that and make use of that. And there's some advantages to that model, especially as you look at SoC design. But we also built in the standard UVM RAL layer and allowed IP exact definitions to basically be able to drive that RAL layer. So you get back to the sort of standardized mechanism for reading and writing registers that the UVM guys prefer. And frankly, it's a very solid, good mechanism. So to create these kind of models, due to the time constraints today, I can't get into a lot of detail on this, but you can see a lot of this on the Breker website if you like. But essentially, we can use these nice graph-based models that allow for a very easy depiction of the test generation that you want, the tests that you want. And then underneath each of these blocks, put in a piece of code like this that makes use of PSS, but with this system Verilog overlay that allows you to use registers in this pretty standardized way, constraints, and so on and so on. We can apply this to an existing UVM test bench with a pretty simple mechanism that just works with simulation. And again, this looks a lot like what Tim and Reese presented, where you pre-generate all the tests into a transaction file using TLM, and then the TLM file is driven into the actual design through the UVM VIPs or agents. And then you can just switch on basically a sequencing mechanism, and the virtual sequencing is included inside this mechanism. The scheduling is all synthesized as well. And if we run the simple tests, we get something that looks like this in a window, and we can actually see these transactions being executed, and they're self-checking, so the scoreboard's included as well. Looking at slightly larger design, such as a DMA operation on an SoC, we can see a similar kind of format, graph-based. In this graph, the data flow goes from left to right, control top to bottom. And again, each one of these blocks can be written out in a very sort of standardized kind of UVM-style fashion and applied through the synthesis tool very easily. The application of this to, in this case, the subsystem, very simple, where the processor is replaced by some VIPs driving, most commonly an AXI bus or something like that. And the same transactions are applied through this and sequenced in the same fashion. So you can see here that it's exactly the same kind of model, and the same kind of model can be applied to basically one simple piece of IP or a full-blown subsystem, and indeed a full SoC as well. And then if we actually run this test, you can see now we have multiple ports and the VIP that replaces the CPU all being driven, again, with the same kind of testing approach. I mentioned path constraints. This is a mechanism to provide abstract constraints and spread them throughout the path from the design. So they can be applied across in a temporal nature across time, and at this very abstract approach, and replace some of the constraining that we sometimes see, which can make general node-based constraints very, very complex to manage. And I mentioned at the beginning, we see more and more issues at this SoC integration level occurring, and one of these is indeed trying to reuse UVM tests at this SoC level. So if we take our solution we have today at the UVM level, it's very easy to pass these system UVM tests and apply them to the subsystem, complete with CPUs, and making use of the C generation to provide CPU programming along with transactions for the ports. And of course, the whole thing can now be run on emulation because of the pre-randomization that we're doing before. So this makes it very easy for a UVM guy to maintain their current UVM environment and keep that working without changing it at all, but create these system UVM tests that be synthesized for the UVM environment and then ported to the SoC level, solving one of these big problems that we see quite a bit, where SoC engineers are requiring or requesting tests from the UVM guys, and these tests have to be modified and changed to make them work at the SoC level. A lot of that can be eliminated, and this makes it much more streamlined for the UVM engineers. So that's basically the end of the presentation. This is just a really brief overview for what we've done. We do have a workshop. We're actually rebuilding it right now. We'll be releasing that on our website, which gets into more detail of the language and the way it operates. But I think that's hopefully provides just a quick sense of what this is all about. And if there's any questions, be happy to take them.
Yeah, thanks, Dave. There's a couple of questions that we've got, and I'll go into those now. So the first one is, I think it's about the theme of today, because we've seen a theme of trying to separate out concerns and verification. So, I mean, the standard approach at the moment is to generate everything and run it in SVUVM, or some people still using SpecRAM, I suppose. Some people use Python, and some people are using VHDL, but most of the industry is using SVUVM. to do everything. So why do you think there is this now, this trying to delineate?
Yeah. Well, so that's a great question. And I think, honestly, I think Tim answered it already even more effectively than I can, right? So I think as these designs get more complex, by separating out the concerns, as you put it, right, and trying to figure out the randomization up front, and then the application to simulation later on, and breaking those two things up, it actually simplifies the whole general problem. So now what we can do is, you can figure out coverage constraining early on and not worry about that later. You can make sure that the tests themselves can be configured more effectively, can be constrained more effectively, and things like that. And I think it plays well with emulation and prototyping environments that we see in use, more and more these days, right? Because emulation is in the past has been restricted to sort of the back end of the process and using real world kind of workloads just to see if you can trip over a bug that hasn't already been spotted. Now we can bring emulation up front and use it by randomizing early in the process. And that allows us to do much more thorough testing, finding difficult, complex corner cases in designs that otherwise it's very hard to pick out. So I think it's that. I think it's a separation of the issues to allow you to sort of code and manage these in a more straightforward fashion, and the use of execution platforms like emulation earlier in the process to give you more performance, more ability to find these corner cases.
Okay, and there's another question here. One thing that was hinted at, I think, by Reese, is that you can actually also separate out the skills, and he pointed out that there's quite a lot of SV UVM people. I guess
Yes.
we would have said 5 years ago there was a shortage of them, but maybe now there's more. And so they try to separate out the skill base. Do you see that going on as well?
Oh, absolutely, yeah. And in fact, that's part of the driver behind this. So we've introduced this portable stimulus language, and I think there are a lot of people that are picking it up, and it has a lot of power, especially at the SOC level. So I'm not trying to knock portable stimulus. However, there is a need. Well, so a lot of engineers do have a system Verilog UVM background these days, and leveraging that and making it easier for those engineers to apply these sort of more modern techniques, I think is critical. Which is why we've sort of produced this idea. And this was customer driven by 3 very large customers of ours who said, it must be in the same way we put UVM on top of System Verilog, it must be possible to do something like that with PSS and make it easier to learn and easier to sort of figure out for these UVM engineers. And then, of course, once you've done that, you can easily go on to sort of do a broader, more powerful PSS kinds of models for SOC and beyond.
Okay, and that takes us perfectly up to the end of your time. So thank you very much.